Hello, my name is Albert Merquin. The concept that we're going to talk about today is called arc flash incident energy evaluation or arc flash auto evaluation. This concept was born a couple of years ago from an idea that I had while thinking about how to improve the methods that we had available to evaluate the incident energy. Well, this method or concept relies on evaluating the incident energy using time current characteristic curves. So let's get started with what we would like to cover today during this webinar. First, I would like to explain how the industry in general can benefit from the concept of arc flash auto evaluation. It is really important for everyone performing arc flash studies to understand that this evaluation is taking place ahead of an arc flash study, and hopefully as results of the evaluation of the C area and arc energy damage points, the scope of the arc flash study can be reduced or even eliminated altogether. Before we get into the evaluation details, I would like to explain the key concepts behind the arc flash evaluation, which is the C area plots. The C area plot is a brand new concept which was first presented last year at PCIC Vancouver by myself and my co-author Anthony Parsons from Schneider Electric. We will also take a look at the theory behind the evaluation of the arc energy damage points during this webinar. Once we understand the details and the theory behind each of the components that we're evaluating in arc flash auto, I would also like to present to you with some live examples of the arc flash auto evaluation tool in ETAP and how it can be applied to a variety of different applications in our everyday analysis of power systems. The main driver for the research and eventual publication of this new concept is the fact that I really wanted to help to reduce the number of systems which simply go unanalyzed. Study budgets many times do not allow the arc flash study to reach certain portions of our power systems. The other main concerns that I wanted to address with this novel concept is that in many countries, arc flash is simply not even a requirement, and these studies simply finish at the protected device coordination and protection stage. Well, that is one of the main purposes of this concept of the C areas and also the arc flash auto evaluation tool. Furthermore, after spending several years of my life working on the development and validation of the new IEEE 1584-2018 arc flash model, it became apparent that our current ways or methods of analyzing the results were sort of inadequate. The enhanced sensitivity of the new model to each input variable and the increased number of variables required modern tools which can help us analyze hundreds if not thousands of possible combinations of these input parameters. The last main driver for this research and development for this particular concept of the C areas is the basic fact that, at least in my humble opinion, 95%, if not more, of all the arc flash studies being performed out there use typical input parameters provided in the standard. I know that we worked in the committees very hard to develop the typical data tables during the writing stage of this new standard. However, in many cases, variations in these input parameters cause the arc current and incident energy to operate in regions or forms that are not typically expected. As we will see during this webinar, the C area plots allow us to see the arc flash incident energy from very different perspectives. As I mentioned before, and to recap, the main purpose of arc flash auto evaluation is to detect high incident energy levels during the early stages of our protected device protection and coordination stage. Before we get into the background, the last main item I would like to generalize is that the concept of C areas is applied to radial systems, but it can and it will be extended in the near future to multi-source or loop systems. In near future releases, fortunately, the majority of our systems which go unanalyzed are those low current, low voltage radial feeders, and thus this tool applies to them directly. Some additional benefits besides those already mentioned are the significant reduction in the number of arc flash study scenarios and the potential reduction in the data collection for certain portions of our power system. Before we discuss the details of our more advanced and complex concept of the C area plots, I would like to discuss by watching some videos and explain the concept of equipment damage evaluation, in particular for arc resistance switchgear. In this slide, we can see the main effect of the buildup of energy. We can see that one more time. The main concept that we're trying to understand from this video that we just watched is that when evaluating arc resistant equipment, is that we're trying to determine if the equipment can handle a certain amount of energy buildup internally. Just because an equipment is arc resistant, it does not mean that it can handle any amount of energy flux per unit second. The pressure buildup is proportional to the arc power and time. As we can see in this video, both faults carry similar amounts of current, but their duration is significantly different. If the fault or arc fault remains in the equipment for a long time under a current which is high enough, eventually the equipment could fail to vent or to even contain the arc plasma and molecular cloud away from the front of the equipment. Also, if the arc energy inside the equipment is too high, it may prevent from placing the equipment back in service with a basic cleanup and reconditioning, as is what is expected for an arc resistance equipment. The most important takeaway from this video is that energy is proportional to arc duration or time and current, and if either parameter is too long or too high, then the arc could exceed the equipment kiloamp cycle rating. Now let's look at an example of the arc energy equipment damage evaluation. In order to evaluate this damage point, we must obtain the rating from the manufacturer and plot it on a time current characteristic curve or TCC curve. As we can see in this particular slide, we see a representation of the TCC with the arc energy damage point, which is 50,000 amps with a arc duration of 500 milliseconds or half a second. This rating represents a 1500 kiloamp cycle amount of energy for which this equipment is expected to operate within its design capabilities. The next step, that is perhaps the most important step in the evaluation of any kind of arc flash condition, and in particular in this case we're evaluating the arc resistance characteristics of this equipment, we must establish an accurate short circuit range, or the available voltage fault current range for this particular location. Once we've determined the voltage fault current, we can determine the corresponding arc currents, both minimum and maximum values. Once we have determined this minimum and maximum arc current values, we can proceed to perform evaluation, and we're going to evaluate over the range of the current. The first evaluation at the minimum combination of arc current and time shows that the area or energy released by the arc for that combination of current and time results in an area which is smaller than the area of the equipment rating. This is considered as a pass for this evaluation at this point. In the same token, we can evaluate the maximum arc current and minimum arc duration, and therefore also observe that the area of energy released for this particular combination of time and current is also smaller than the rated energy area of the equipment. Therefore, this is also a passing evaluation. Last, we can evaluate specific arc currents and arc durations. In fact, if we proceeded to have executed an arc flash analysis on this particular location, we would have found a specific single solution of arc current and time. Using that particular current, we can evaluate the response of the protected device, and if it is less than the maximum arc duration rating for this arc resistance switchgear, we can also consider this a passing evaluation. To summarize what we have seen in the last two slides with videos and now this example on our TCCs, the concept of evaluating the arc energy damage point on equipment consists of two phases. The first phase is evaluating the incident energy and the energy released over time and comparing it against the rated energy of the equipment, represented by the kiloamp cycle rating of the gear. And second, we must evaluate the response of the protected device at a specific arc current times to make sure that the duration of the arc does not exceed the maximum rated fault duration for the equipment. Now that we have under our belts the background for equipment arc energy damage point evaluation, we can start the discussion on the C area plots. C area plots really are a multi-C line combination. Hundreds of C lines can create the C area covered by the C area plots. However, the use of C lines, as the industry has used over the last couple of decades, is limited, and really it is inadequate for capturing all the potential variations in the construction of our equipment, of our different types of equipments. C lines in reality represent only one or a single combination of the input parameters that we use when we perform an arc flash analysis. There are thousands of potential variations in the equipment construction, and in reality it becomes very impractical to analyze them using single lines. This is where the concept of the C area plot was born, out of the necessity to try to capture all of these variations without introducing labor-intensive analysis using multiple sets of lines, which represents the arc energy at different electrode configurations and so on and so forth. This multiple line analysis could also introduce error in the evaluation. The concept of C area was really introduced by myself and my co-author Anthony Parsons during PCIC in Vancouver in last year, 2019. And this was a novel concept that introduced to the industry this application for evaluating a constant energy or reference point on our TCCs. And that is the concept that we're discussing next. The C area plot by itself allows us to be able to analyze multiple forms of the arc or the arc flash, depending on the amount of current. An arc could become an arc flash, without having to switch the input parameters to multiple combinations. In reality, an arc inside any piece of equipment can take on multiple forms. Very rarely will an arc flash within an equipment behave exactly like what was used in the test setup in the actual laboratory conditions. Therefore, for any one location, it is unlikely that the arc could take on different forms, and thus it is necessary to consider how each form of the arc could impact the response time of the upstream protected devices, or the opening time of the upstream protected device. The C area plots also allow us to represent all locations and enclosures of a particular piece of equipment, and also to evaluate it from the point of view of a single upstream protected device. There are many applications for C area plots, but in particular, manufacturers could in reality publish a single sea area plot, which would represent a single equipment model, and then designers or study engineers could use that to evaluate the entire equipment for arc flash conditions. Now that we understand the benefits and where the concept of sea areas were born or came about, we can quickly step through the review the sources of variation. Inside of every enclosure, we may find any one of 3 different enclosed electrode configurations as described in IEEE 1584-2018. Sea areas can consider 1, 2, 3, or even more electrode configurations automatically. Therefore, there is no necessity to repeat multiple arc flash scenarios accounting for the effect of each electrode configuration within the equipment. The sea area plots algorithm allows us to combine multiple electrode configurations and conservatively evaluate the effect on both current and incident energy for each combination. The open area electrode configurations that are also described in the standard, although apparently not considered in most enclosed equipment, could also be present to an extent within our electrical equipment, enclosed equipment. In fact, one of the most unique benefits of the sea area plots is its ability to actually represent graphically the effect of having an electrode configuration which makes the arc current behave like an open air condition. But in fact, the incident energy release of that arc could also behave more like that of an enclosed configuration. Perhaps as intriguing as this sounds, this could be the greatest benefit of the sea area plots. We will see in examples later on during our webinar how this can be explained with physical explanation of the equipment construction. These images show potential examples of equipment where multiple electric configurations are included. The highlighted regions, depending on the direction of the power flow, can either be BCB, vertical conductor in a box, or BCBB, which stands for vertical conductors in a box terminating in an insulating barrier. So any one of those electrode configurations can be present in any one enclosure with multiple gaps or different orientations. Therefore, it is very difficult to consider a single combination or even 2 combinations of these electrode configurations. So the sea area plots in general can handle unlimited number of combinations and help us visualize the impact of these combinations on our incident energy calculations. Another factor or another source of variation which is automatically considered by the sea area plot algorithm is the arc current variation. Because of the positioning and orientation of the electrodes in the configurations that I mentioned earlier, the arc current can vary significantly. In particular, in low voltage equipment, the variation can be as high as 15%, and in medium voltage, the variation can be as high as 3.5 to 4%. The variation is automatically accounted for in the sea area plot algorithm. Another major source of variation, which is difficult to capture and many times ignored, is the gap between conductors or the gap between electrodes at different sections of the equipment can vary significantly. In fact, it is very possible that within the same enclosure, we can find gaps of 1 inch all the way up to 6 inch. And the variation of these gaps has a direct effect on the arc current. Longer gaps will introduce higher voltage drops and therefore reduce the arc current magnitude. Shorter gaps have the opposite effect. This increase or decrease in the arc current can have a profound effect on the duration of the arc. One very popular source of concern as well, when applying the new IEEE 1584-2018 model, is the determination of the proper dimensions for each location. This new standard has introduced the dimensions as an input and as a direct parameter in the calculation of the incident energy in the equipment. However, it is very unlikely that we're going to measure and capture the width, height, and even depth of each particular enclosure and represent the equipment one enclosure at a time. Of course, ETAP has the capability to represent multiple enclosures with very specific dimensions. However, when we're evaluating the design of the protection and coordination of our system, we may need a tool that relates all these particular combinations in one chart. The C area plot has the capability to represent all these combinations in a single area. In the previous images, we saw only examples of the width and the height of the opening area of the enclosures. In this particular example, we also see that the depth of the enclosures has a significant effect, in particular for low voltage equipment constructions. Also, if the variation of the depth is specified, the C area plots can account for the effect of the depth in the incident energy representation of our C area plots. Many times, arc flash studies are only done based on single working distances for each voltage class. Typically 18-inch or 24-inch in low voltage and 36-inch for medium voltage and high voltage. However, with the concept of C areas, the engineer in charge of performing the analysis can perhaps specify an expected variation on this working distance. As we can see in this particular image, the electrical worker can change its distance by either approaching the equipment to perform certain movement or task, or increasing the distance by moving away. In reality, the C area plots can capture both variations, either an increase in working distance or a decrease in working distance by a certain percent, and therefore account for potential higher incident energy exposures. This is a good benefit of the C area plots because it prevents us from having to run multiple arc flash calculations at multiple working distances. So now that we've defined the individual sources of variation in graphical form by means of images and descriptions of what the physical parameters are, we can put them and translate these variations into actual parameters. So we can see in this list that we have the voltage as an input. We have also the gap, delta G, delta D, which stands for the variation in working distance, delta CF, which is the variation in the enclosure size correction factor, which is composed of the variation on the width, height, and the depth of each one of our enclosures. So delta CF is in reality a compounded variation of three individual variations that are taking place. On top of that, as we saw at the beginning of the concept of C area plots, the variation introduced by the electric configurations is significant. We could have many electric configurations within a single enclosure. Last, naturally, because of the electric configurations, we also have a potential arc current variation to deal with. So next, to better be able to understand the concept of C area and how C area plots are evaluated, we can do an example for a low voltage switchgear. As we can see in this diagram, similar to the images that we saw before, the dimensions and gaps of the equipment can vary significantly from different location and in different compartments. In this particular example, we see different enclosures of different heights and widths and also depths. Having considered the variation in each width and height, we can proceed to give numbers to these variations. And this is also a very important step in the application of C area plots, which is to identify what is the range of variation on each of the parameters for the C area plots. Fortunately, ETAP engineers perform months of research on different types of equipment for different voltage levels and compiled a range of variations for each type of equipment. This default variation values for each type of equipment is included in the auto evaluation program as typical data that can be applied to different types of equipment. But now, having said that, we can continue with the example. And this table shows that we're going to do a low voltage switchgear where the voltage is 480 volts, and we're going to apply a variation of plus or minus 10%, which is typical for low voltage equipment. The gap variation is plus or minus 30%, working distance only a reduction of minus 10%, height, width, and depth all with a plus or minus 20% variation, and also we have potentially identified that the maximum short circuit current is 20,000 amps and a minimum value of 4,000 amps. The electrode configurations automatically configured in this example are BCB and BCVB, and the target reference energy is 6 calories per centimeter square. So this is where the magic of the C area plot happens. First, let's look at what a C line used to look like in previous versions of ETAP and how the industry has applied it over the last couple of decades. First, we will start with a TCC characteristic, which represents the starting end and the end point of the line. Next, we would proceed to plot the line and refer it for a constant energy value of, in this case, 6 calories per centimeter square. And this is what the industry has been using to evaluate the incident energy. Of course, if we evaluate this line against an overcurrent relay 51 function, we can see that it actually passed the evaluation, no problem. This single combination of parameters only allows us to see one possible outcome of the arc flash within this piece of equipment. Of course, as we now know, there are multiple outcomes, multiple possibilities of the arc within that equipment. So now if we apply the variation on the gap between conductors, which is approximately plus or minus 30%, we see an increased number of potential points where that arc could live. At the same time, if we apply a different electrode configuration, we see that the potential variation in the arc has also increased to different points. Some lower current with higher clearing time requirements. Continuing on the trend, if we apply the height, width, and depth and working distance variation, we see that the number of possibilities of the arc has extended significantly. And last, we can define a boundary for our C area points. This is the boundary of the combinations we yield the lowest current and higher incident energy, lowest energy, and lower currents. This boundary area now represents all potential combinations and forms that this arc can live with within that equipment and allows us to set a constant energy value to it. If we perform similar evaluation as we did in the past, we would see that the evaluation actually fails, which is the reason why a single line cannot be used to evaluate the energy response on a time current characteristic curve. This failure is caused by the fact that the arc can live in different forms with longer gaps and different electrode configurations. Therefore, an adjustment of the time dial settings for this relay will be necessary in order to accommodate these other potential forms of the arc. Next, we can look at another example that I mentioned earlier during our webinar. And it is that this C area plot allows us to look at the arc in forms that even with the equations that we have available in the standard, we cannot look at. So in this particular example, we look at a very basic equipment enclosure where we can identify electrodes in the BCB orientation. As we can see in this particular case, the box size and the electrode arrangement are very similar to our BCV configuration. Therefore, the C area curve that we see here representing an 8 calorie per centimeter square reference point is easily cleared by the main low voltage power circuit breaker. Therefore, the result of this evaluation would be a pass because the upstream protected device protecting the low voltage switchgear would clear the fault from maximum to minimum range of this particular C area plot. However, what would happen if in fact this piece of equipment looked very different? What if those electrodes had a significant amount of space below, from the end or tips of the electrodes down to the lower surface? This could potentially allow the arc columns to expand or elongate to a significant length. This elongation could make the actual arc current behave more like that current that you would get under a vertical open air condition. And however, eventually the plasma cloud and the plasma will build up inside the enclosure and come out the front. So therefore the energy release would still behave like that of a box. Our regular equations do not allow these combinations. However, the C area plot will allow us to evaluate this condition. And if we evaluate this condition, we can observe that this will be a failure because under some forms of this arc, the arc current could be so low that it could potentially take a very long time for the arc to clear, and therefore make the work around this equipment be potentially unsafe for some combinations. Here we can also see where the original BCB, vertical conductor in a box configuration, which was the only electric configuration in the original evaluation, is located with reference to the new revised BCB plus VOA configuration. This is actually a unique feature of the C area plots, which cannot be captured even with a regular arc flash simulation. Next, we can move on to a live demo of our C area plot evaluation and also our equipment arc damage point evaluation in our new ETAP 20 version. For our first live demo, I would like to utilize this example system, which contains low voltage, medium voltage, both 5 kV and 15 kV and 480 volts. In order to perform the arc flash auto evaluation, we must switch to the protected device coordination mode or star view mode. Once we switch to this particular mode, called star protection and coordination, we must do a few other things before we can perform the evaluation. The first thing we need to do is to make sure that we go to the study case, and in the study case we can go to a tab called Star Auto. In this particular tab, as we can see in ETAP 20, we have added a new section, a group box section called Arc Flash Evaluation. In here we must enable the Arc Flash Evaluation. For this particular case, we will do both arc flash and star coordination at the same time. Therefore, we don't have to use the arc flash only. However, in the next example, we'll see how we can utilize or take advantage of the arc flash only option. Also, now that you've enabled the evaluation, we must also select a rules or a rule book selection. This rule book tells us how to evaluate the C area plots and the equipment damage points. We can use the default ANSI/NEC rulebook and click on the View button to quickly be able to inspect the rules that we have for this particular system. We can select the Arc Flash tab and quickly see that we have rules for both C area and arc energy damage points. And of course, we see that we have enabled the evaluation of the bus side, line side, and low side, and we have another slew of options that we will discuss as we go through this webinar. Bottom line, to summarize this particular section, we must select a rulebook and we must enable the evaluation of the arc flash in order to be able to run the simulation. Once we've done these steps, it is very simple to run the simulation. We can select Control A and perform a global evaluation for every point, or we can simply select a group of locations and run the evaluation. In this case, I click on my group of buses, and all I have to do is click on the Star Auto Evaluation button on the right-hand side toolbar. As the simulation runs fairly quickly, we can see that we get our Star Auto Evaluation Analysis Viewer, which contains a grid for the results and also a TCC view, which is a temporary view where we can make adjustments and settings to the particular protected devices. In this case, we have several tabs: general, bus, cable, generator, load, motor. We're going to focus, for the sake of brevity, on the general, coordination, and arc flash tabs. Switching to the coordination tab real quick, we can see that every coordination evaluation between our protected devices is a pass. That means that we have done our job on coordination and we have a proper graded time differences between operations of our protected devices selected into this particular project. However, as the topic of our webinar today is, we are really looking at the arc flash evaluation. And as you can see, this new tab that has been added to the arc flash to the Star Auto Evaluation Analysis Viewer, shows us the results of an actual evaluation of the C area curves and the arc damage points for the equipment. As we can see, we have several passing and failure results. Let's start by looking at some of the passing results. By simply clicking on the corresponding protected devices on the grid, we immediately see the passing results denoted by this passing symbol on the grid. Here we can quickly see that a passing condition simplifies that the C area curve is basically above the expected opening time of the protected device. In this case, for all the load side of the load circuit breakers, we have a passing condition. Same thing for FD7, same thing for FD3, FD2, and FD1. However, when we come to the bus side, as we click on the main power circuit breaker, we see that for the bus side fault, we have a problem. We can observe right away that there is an overlap between the C area curve and the low voltage circuit breaker LVSST unit or trip unit. In this particular case, this overlap tells us that we will have energy higher than 4 calories per centimeter square. And the same is true for the line side of the main circuit breaker, in which we see that the energy is potentially higher than 8 calories per centimeter square. In this particular case, we notice that there is no overlap of the relay curve with the C area curve. However, when you account for the delay, lockout time, and other delays, plus the breaker opening time, it is very possible that that combination of total time exceeds the limit and incurs into the C area region. We can quickly solve this and understand that we're perhaps at the lowest setting for this particular protected devices, so we cannot lower anymore the time dials and make adjustments. Any adjustments would violate the coordination settings that we have prescribed. Therefore, to solve this particular location, the issues with this particular location, we could quickly change the reference energy values so that we understand that for this particular design and this particular type of protected devices, we cannot limit to 4 and 8 calories per centimeter square accordingly for the bus and line side. So if we quickly double click on the bus and proceed to go to the C area curve, we can simply click on the settings button and make the adjustment accordingly. 12 calories for the line side and 8 calories for the bus. Having made this adjustment, we notice that automatically the evaluation tells us that the energy will be 12 calories or less on the line side, and it will also be 8 calories or less on the bus side fault. When we perform an arc flash analysis in the future, if we ever have to do this, the result probably will be slightly smaller or 8 calories or less. Now that you see how simple it was to correct this, we still observe that the coordination tab shows that all our coordination settings still have not been changed and we have no violations on the coordination practice. Going back to the arc flash grid to evaluate the results, we can see also that we have an example of the arc energy damage point violation. In this case, this 5 kV switchgear is a arc resistance switchgear, and we have the particular ratings shown on the TCC. In this case, 50,000 amps for half a second, or basically 1500 kA cycle is the rating in terms of energy for this particular switchgear. We see that the evaluation is a failure because the arc duration critical limit is exceeded. In this particular case, we can try to fix this by simply seeing if we still have some margin on the time dial differences between this relay and its upstream device or downstream device. We can simply lower the time dial on the relay by a couple of settings and observe if our arc resistance switchgear rating is now passing. In this particular case, we observe that the changes we made automatically tells us it's a passing for the arc flash criteria and the equipment damage point, and at the same time we can go back to our coordination and we see that we still maintain a proper distance or difference between the two relays, therefore we still have coordination in our system. Going back to our arc flash tab, we can proceed to look at a higher risk area, the 15 kV metal clad switchgear. where we have a couple of violations. First of all, on the low side of these particular switchgear, on the low side compartments, we notice that we have an energy that is higher than 12 calories per centimeter square. At the same time, we look at the bus fault on the main circuit breaker compartment CVAM, and we observe that our limit of 25 calories per centimeter square, which is what we have PPE for, is also exceeded. For this particular location, we can look and evaluate the equipment construction and determine if the particular settings used to represent the C area of these particular locations are in agreement with what we expect from the equipment construction. For that, we can actually proceed and inspect the low side fault. As you can see, the low side fault shows us that we use a C area curve that has a BCB and HCB configuration as shown in the legend. In this particular case, if we double click on the C area curve, it will take us to the location where we have the C area. But before we make any adjustments to it, let's take a look at the rating page. And for this particular equipment, we are lucky and we do happen to have some images or graphics of the actual location we're dealing with. So in the case of this circuit breaker CVAFD, where we're evaluating the low side fault, we can immediately proceed and observe that this particular enclosure happens to be the low side enclosure below the low circuit breaker. In this particular location, we do not see an obvious horizontal conductor in a box configuration, but we can observe a vertical conductor in a box configuration. Therefore, we could revise the C area settings accordingly to see if, under the assumption that we only have BCB in this particular location, if we can actually continue to use the current protected device settings on our relays. By simply clicking on this C area curve editor, we can proceed to go to the low side and automatically make the adjustment. Notice that our electrode configurations are both BCB and HCB with proper gaps and height and width and working distance variations. We could try to reduce those as well. However, in our opinion, only the removal of the worst case condition HCB for this location perhaps will do the job. By clicking OK, we can automatically see that in this particular case, this location is now a passing, and our incident energy is expected to be perhaps far lower than 12 calories per centimeter square. However, if 12 calories per centimeter square is the PPE that we have available, it should be safe for use on this particular location. Last, we can go and switch back to our coordination and see that so far we have not made any changes on this particular location. So perhaps going back to relay 2, we could try to make a couple of adjustments. Perhaps we can lower the settings on the instantaneous delay, but at this case it probably seems that we cannot do that. So we can perhaps go to the next location, which is that of the bus side fault, which is marked by 25 calories per centimeter square. In this particular case, if we look at what enclosure we're dealing with and as how you account for the variation at that location, we can also go back and understand that we have some limit violations, so we have to investigate and make better assumptions as to how we select the C area plots. In this particular case, if you go back to our graphics that we have for this location, we can go now to the main breaker and observe that this particular enclosure, we're inside the main circuit breaker, and we do have potentially a horizontal conductor in a box inside the cylinders for the stabs of the circuit breaker. This particular electrode configuration could release a high amount of incident energy, and therefore, unlike the previous example where we were able to dismiss the HCB configuration, electrode configuration, in this case we cannot. Therefore, under this condition, with the current settings and with the current time delays that we must allow for the coordination of our system, perhaps the only reasonable initial evaluation for this location is to mark it as a high energy location, and therefore perhaps recommend that we add some sort of incident energy mitigation equipment on top of this. Perhaps some light detecting relays or a faster trip device operation, or whatever the technique that we decide to use, perhaps differential protection. However, in this particular location, to reduce the incident energy, or to mark it as a passing, we must identify what energy level we could limit based on our normal overcurrent protected device settings. By double clicking on the C area curve, going back to our settings tab, for this particular location, we can see if our 40 cal category suits will allow us to work on this location. In this case, as we can see, 40 calories is actually a borderline or a marginal limit. What it means is that we're within 95% of the 40 calorie limit for some combinations of these parameters on this area curve. So with this, we see that we've actually made changes to settings, to protect the device, relays, time dial pickup values, and at the same time, we've revised the expected reference energy values for several locations. And we've understood the relationship between the C area curves and the overcurrent protected device settings. Now we can move to our next example, where we will talk about the application of the C area curves to different types of systems. In our next example, we'll be using a distribution system. Our next example is a distribution system. For this particular example, as we can see, it is a large distribution system with several substations and different transmission lines providing power to different buildings and small facilities. In this particular simple system, we have probably over 2,000 buses, and we can apply the arc flash evaluation tool to different locations. And for the purpose of our discussion, I would like to focus into an area of this distribution system where we have not performed coordination. But before we do that, and just to illustrate the difference between running an arc flash study and performing a arc flash auto evaluation, what I would like to do is first switch to our regular AC arc flash mode, where I have selected to fault a particular group of buses. Once we run the arc flash or regular arc flash based on IEEE 1584-2018 simulation, we will be able to see for these locations, there will be some locations where the incident energy is very high, and that is because we don't have the proper settings or sizes for the upstream fuse protections protecting the transformers. In other locations, we simply just do not have enough current to cause the upstream protected device to trip. Therefore, there really hasn't been a lot of arc flash settings or studies performed on this system. We could confirm that also by simply switching back to our protection and coordination mode and simply clicking on the same buses that we faulted before, and then we can perform the arc flash auto evaluation. Before that, we can quickly inspect on the study case that we are actually enabling the arc flash option, and we have selected a particular set of rules which are custom. In this particular case, we can observe that we've created our own set of rules called My Rules, where we can modify the particular arc flash auto evaluation settings and preferences. So now that we have done this, we can simply evaluate those locations. And as you guys will see, after the simulation finishes, we will observe that for several locations, the transformer protection is lacking. In other words, it hasn't been performed. Therefore, the pickup, the full load amp or continuous amp rating of the fuses do not match with the corresponding size of the transformer. In some cases, the inrush may be disregarded, in some cases it's not, but for the most part it passes. And also the damage curve of the transformers is not protected. At the same time, obviously, if we don't even protect the transformers well, our arc flash results are going to be extremely high, as you saw from the simulation. But of course, we're trying to emphasize the concept of performing an evaluation of arc flash by using C area curves at the time of the protection and coordination of our system. So now that we know that we haven't done this coordination and protection, we can switch to the transformer tab, and we can simply make adjustments to these fuses to set them to protect the transformer based on the transformer damage curve, and also account for the potential inrush setting, and also account for the size of the fuse relative to the full load amps requirements of the transformer. In this case, we probably selected transformer here, not the proper size for the fuse. And one more time for the last particular group of elements in here, we make our last selection. Now that we've actually managed to protect the transformer, account for the inrush settings of the transformer itself, and properly account for the full load amp rating of the fuse relative to the transformer, we can switch back to the arc flash tab and observe that still we have not reached the desired solution, yet we're close. Our reference limit for arc flash for this particular locations is 16 calories per centimeter square, and therefore you see in most of the cases we're close, but we're still overlapping or touching certain areas of this portions of these areas, therefore we still have violations. So in this particular case, we also needed to do some adjustments on the protected settings of the protected sizes of these fuses. So now that we've done this, we can see that this location passes, and perhaps if we wanted to sacrifice the protection and coordination and give preference to arc flash safety, we could observe that on the transformer we have everything passing, but we could make further adjustments on our selected fuse size in order to improve the response in terms of arc flash analysis. So now we see that we have making further adjustments, and as we complete this process, we see that in this particular case, every location will provide 16 calories or less, potentially 10, 12 calories, or maybe even less. And at the same time, we also observe that we have sacrificed some of our settings. For example, in this particular case, we have selected a fuse that is slightly smaller than the continuous full load amp rating of the transformer on the primary side. Well, it is always a dilemma. Give preference to the coordination or to the arc flash incident energy mitigation. And in this case, we can assume that using a slightly smaller size than usual, it's a better preference because it is the only mitigation technique for arc flash that we have available at this location. So what we just done is an example of performing the transformer protection and at the same time looking at the incident energy that this protected devices would release in the event of arc flash on those locations. Next, what I would like to do as another example is show what would happen when you go into a system where you don't have necessarily all the arc flash settings selected, you have not enabled the C area plots, or you haven't performed the proper selection of the typical data and parameters for a particular system. In this particular substation, we have hundreds of locations where we can perform the analysis, and we can simply make sure that we perform an analysis only from the arc flash point of view if we desire. In this case, we have done some coordination already in this substation. However, we would like to verify that the arc flash results are accurate. So for that purpose, what we could do is we can go into the study case and go to our Start Auto Evaluation tab and click on the arc flash only tab. This will allow us to only evaluate from the point of view of arc flash. This will make the simulation run a little bit faster, and it will also allow us to focus only on the arc flash problems that we have based on the current protected and coordination settings for our protected devices. Also, what I would like to do is I would like to inspect our current rules, which are accessible through the Rules Start Auto Rulebook section. And as I mentioned before, we have a customized set of rules called My Rules that we can edit and we can quickly inspect. Under the Arc Flash tab, we observe that we're evaluating the different C area plots for bus, line side, and low side. And at the same time, what I would like to do is focus more on certain particular locations of our system. For example, based on IEEE 1584/2002, it was acceptable to eliminate out of the scope of an arc flash analysis any location that was fed by a transformer rated 125 kVA or less, operating at 208 volts to 240 volts. Well, that is no longer the case, so therefore we may have to go back and redo a lot of the studies and evaluate the coordination for those locations. This tool is designed particularly for that specific condition, as we may have to go back and revise some of these older arc flash simulations. To do that, all we have to do is simply select the fault current level and also the voltage value. So in this case, anything fed from a 208 volt to 240 volt system, three-phase, and also in the full current range of 5 to 10,000 amps, which is typically what a 125 kVA transformer at 240 volts would provide if its impedance was around 3.5%. So now that we know that we can filter and focus globally, we also have the option to do a global data substitution. So now we no longer have to go location by location and enable our C area plots. We have the ability to globally define data for that. But we'll look at an example of that in a second. So for now, we'll focus only on the reduce scope by applying global filters, which are accessible through our rulebook. Now that we've made these selections, all we have to do is perform Control A on our keyboard, and now we can run the ArcFlash Auto simulation. So what the program is doing right now is looking at the available short circuit current range, and if it happens to be within the 5 to 10,000 amp range that we have specified in the rulebook, and also if the voltage is 208 volts to 240 volts, then that particular location will be selected as an evaluation location. Right now, we've probably done hundreds of points and locations, so we're creating a lot of temporary TCCs and results. But now that it's done, we can simply see that we can expand our results and data grid information. And we can see that a lot of these locations, in fact, don't meet the 4-calorie criteria that we had predetermined. They're close, as we can see here, but they still quite don't meet that energy value. So we can see several examples where the 4-calorie limit that we have respected globally is not met. However, we do have a lot of locations where the 4 calories that we had as reference, it is passing. So we can see automatically several of our locations are acceptable and are within the 4-calorie limit that we might have predetermined was acceptable for these locations. Now, in this case, some other locations are close to 95% of the 4 calories, which may also be acceptable. However, like I said before, we have a lot of locations where we exceed this limit. And in order to work on those locations, we may have to allow for a higher rating of the personal protective equipment. So as a final example on the application of the C area curves for special locations like the ones I just described, we could repeat this simulation by simply going to the rulebook, Start Auto, selecting My Rules, and globally changing the setting, which is an extremely powerful capability and time-saving tool for evaluating C areas without having to go by bus and specifying the data there. So now if we enable the evaluate based on global C area plot data, we can simply make sure that indeed when we click on the edit button, that in any one of these locations, we have actually now globally defined our parameters, our types of equipment, and also defined that we are allowing 8 calories as a new reference value for the PPE that we're going to wear around all these locations. So now that we've done this, we can simply click OK, save those options, close our rulebook, and simply Control A and repeat our evaluation. As we will see, the results of this simulation will show us that a higher number of locations pass the evaluation, and therefore in any one of those locations it should be acceptable to have a 8 calorie per centimeter square ATPV rating of the personal protective equipment or higher as allowable by the work procedures for these locations. So now that we see, we have our results of the simulation, and we can see that just about 95-96% of all the locations are within the 8 calories per centimeter square solution. So we can quickly inspect some of those locations, 8 calories, 4 calories, and so on and so forth. So now we see that only a few selected locations exceed the 8 calories, but in fact, as we can see in this region here, they do not exceed it by a significant margin. So it is expected maybe 8.5, 9 calories in some locations, but for the majority of the locations, it will be 8 calories or less. So now I would like to move on to summarize and provide conclusions on what we have learned during this webinar. So what have we learned today during this webinar? We've observed that the concept of C area, which is a unique concept that was just introduced to the industry recently provides a extremely powerful way to detect high incident energy conditions during the protection and coordination stage. This is perhaps the most important value because we do not have to wait until we go or get to an arc flash analysis study to detect high incident energy conditions, but we can address most of them during the settings selection for our protected devices. We have also observed and seen during the presentation that arc flash auto evaluation time-saving solution, which significantly reduces the scope of an arc flash analysis. In fact, by allowing and evaluating a sea area plot, we have performed at least 3 or 4 independent scenarios which would be required during an arc flash study. Maximum, minimum, average, normal conditions, they're all covered with a single arc flash evaluation using this tool. And last, since the sea area concept is a novel concept and it's extremely powerful, its algorithm allows us to create combinations of electrode configurations and equipment input parameter variations which cannot be captured even by an arc flash study on its own. So this concept of arc flash auto evaluation for sea area plots and for arc energy damage points of equipment is a tremendous and unique new capability of the ETAP family of products. With this, I would like to say thank you for joining us today. I know it's been a long hour of plus of instructional material, but I hope that today we managed to take away a lot of good learning of concepts and also understand how the new technology for arc flash evaluation is evolving in the direction of anticipation of the problems during the protection and coordination stage. Thank you very much.